Okay, y'all. So, first of all, I hope everyone's doing well. And I want to remind you that in order to do this particular lesson, you are going to need to know how to use synthetic division or long division, but really both, okay? Because I know they are interchangeable for the most part, and for the most part, synthetic division is usually a more concise way of doing things, a little bit neater too. But sometimes long division is important to have as kind of just another tool in your tool belt that you can use for factoring and dividing polynomials. Okay, so that's just something to keep in mind. Make sure you know that. But I guess if you were to pick one to really focus down on, synthetic division is probably the best one to do. But again, it is nice to have both. Okay, so the remainder and factor theorems, that's what we're going to learn, but we're just going to kind of discover for right now. Okay, so this first polynomial, okay, is that f of x is equal to x cubed minus 3x squared minus 4x plus 12. Okay, now this graph over here is actually that exact function. Okay, now I know before with polynomials we were kind of estimating and just kind of getting the gist of it. But for right now, I'm telling you that it is important for this particular lesson that this is the exact graph. Okay, so this is the exact graph for that function. Okay, so the first thing it asks us to do is this. We're going to do f of x divided by x minus 3. Okay, so we are taking this polynomial and we're dividing it by x minus 3. Okay, so hopefully, again, we've done that synthetic division, and that's what I'm going to do here. Okay, so I'm dividing, I'm taking this polynomial, dividing by that, so I'm going to go ahead and write 3, okay, and then I kind of do my box like that, and I've got two layers of numbers. Okay, and what that first layer is, it's the coefficients. Okay, so it's 1 is my coefficient here. Notice one thing I do want to mention. These are kind of decreasing in order, so it's x cubed, then x squared, then x, and then a constant. If it's not like that, you've got to fill it in with zeros. Okay, I just want to mention that. So if it was a gap here, right? If it had x cubed and skipped to x, you would have to put a 0 for that coefficient. Okay, but that's not the case. So we've got a 1 for my coefficient out front, negative 3, negative 4, and then a 12. Okay, and so for synthetic division, okay, the way we're going to start it is we first bring down that first 1. Okay, that's always going to be the first, or whatever that number is. Okay, if it was a 3 or something, we'd bring that down. But you're always going to bring that first number down. Okay, so once we do that, we do the same thing over and over. So it's 3 times 1 gets me 3. Okay, and then we add these two once I get this number here. So I did 3 times 1 to get 3. So negative 3 plus 3, that gets me 0. Okay, 3 times 0 gets me 0. Negative 4 plus 0 gets me negative 4. And then I have 3 times negative 4 to get me negative 12. Okay, so if you remember, that is your remainder. Okay, and if we were to find the rest of the polynomial, right, it's x cubed divided by that first one. So this is x squared. Okay, and then plus, I'll go ahead and write it, plus 0x, and then minus 4. Okay, so that is what f of x, this particular polynomial divided by x minus 3 is. There it is. Okay, now let's go ahead and look at what we have over here. Right now, that's all it's asking us to do. Let's go ahead and look at what we have over here, f of 3. Okay, so we are evaluating this function at x equals 3. So we're just going to, instead of writing x, I'm going to write a 3. So I've got f of 3. So I've got 3 cubed, okay, minus 3 times another 3 squared, okay, minus 4 times 3, and then plus 12. I'm just filling in, instead of x, I'm plugging in 3. So 3 cubed, that's 27. Okay, this ends up also being 3 cubed, right? Because 3 squared is 9. 9 times 3, so this is minus 27. We got 4 times 3, that's 12, and then plus 12. Okay, so this whole thing ends up being 0. Okay, and then we're going to go ahead and graph it. Okay, so let's go ahead and look at the graph, just see what's going on here. So mark the points on the graph where x is equal to 3, so let's go find where x is 3. So 1, 2, 3, here it is. Okay, and then I'll write the coordinates like it's asking, and we get 3, 0. Okay, so we're trying to kind of find a pattern here and see what's going on, but you notice that the remainder was 3. The remainder was 0 here. Okay, and then when I input 3, I also got out 0. Okay, so let's continue to kind of, we'll kind of keep that in the back of our mind, but we're going to continue forward. Okay, we've got f of x divided by x minus, or x plus 1. Okay, so same function, and we're dividing x plus 1. Could you do long division? Sure. Okay, but synthetic division is definitely a little bit quicker. Okay, so we've got negative 1. And then same numbers up here, 1, negative 3, negative 4, 12. Okay, we pull down that 1. Okay, now we multiply. We got negative 1 times 1. That's negative 1. Now we're adding these two, so negative 4. Negative 1 times negative 4. That's positive 4. Okay, and then add these two together, so I end up with 0 here. Okay, and then negative 1 times 0, that's 0. Okay, and then we add these two up to get 12. So this time my remainder is 12. Okay, so a couple different ways to write this. One is, I know in one of the videos it mentioned like writing 12 over x minus 3. You could do that, or you can just kind of write how I'm going to do it, which is as follows. So we've got that this is equal to x squared, okay, minus 4x, and then I'm not going to write this plus 0, okay, but I am going to write remainder, okay, like r 12, okay. So that's kind of another way to write it. Mathematically, if we were being mathematically, like super mathematically precise, maybe we would want to write it in the way that one of those videos mentioned, where we would put 12 over x plus 1 in that particular one, since we were dividing by x plus 1. Okay, so we'll keep that in mind as we move forward, and let's look what happens here. Okay, f of negative 1. Okay, so f of negative 1, instead of x up here, I'm going to write my negative 1 cubed, minus 3 times negative 1 squared, minus 4 times negative 3 plus 12. So let's see what happens. Negative 1 cubed, that's negative 1. Negative 1 squared, that's positive 1. Okay, so positive 1 times 3, that's just minus 3. Okay, because I got to keep that negative since this ends up being positive. Over here, negative 3 times negative 4, right? So minus 4, but then times that negative. So this is minus a negative 12, okay, right? And minus a negative 12. So that's going to be like plus 12, okay? And then a second plus 12. Man, I knew something was looking weird. Okay. Rolling with it. Here we go. Negative 4 times negative 1. Okay, that's a plus 4. Okay, I knew something was funky here. All right, and then plus 12. Okay, so now we have the correct one. Okay, we got negative 1 minus 3. That's negative 4. Okay, negative 4 plus 4. That's 0. So I'm at 0 up to here, and then 0 plus 12. Okay, so another 12. All right, something to keep in mind. All right, these are two very different things, but notice a pattern. Okay, and then on the graph, let's go ahead and look at it just to kind of double check here. Let's look at what negative 1 is equal to on my graph. Remember, this is the exact graph of this up here. Okay, so we've got negative 1, and we're going up, and yes, positive 12. Okay, so there we go. All right, so I'll probably go a little bit quicker through this second one. Very similar process, but just to see that pattern maybe one more time, let's go ahead and do this one. Okay, but essentially, I guess maybe first let's talk about it. Essentially, what's going on, right, is you are dividing a polynomial. Okay, you're dividing that polynomial, but the solution for that polynomial, right? The solution. What I mean by that is, where x minus 3 equals 0. Well, x would be 3 here. The solution for that polynomial that we're dividing by, okay, if I plug that into the function, I end up getting out my remainder. My remainders are the same, okay, and so that's why the remainder factor, right, or the remainder and factor theorems kind of have that in common, right? So we divide by that solution. It's the same thing as plugging in that solution in your remainder, and your outcome of the polynomial ends up being the same value. Okay. All right. So g of x g of x. Okay, so let's go ahead and see that pattern again. We've got a plus 4. I'm going to divide by negative 4. Okay, coefficients 1, 2, negative 7, 4. Pull down that 1. Negative 4 times 1, that's 4. Minus 2 here. Negative 4 times 2, negative 2, we've got positive 8. Negative 7 plus 8, that's 1. Negative 4 times 1, that's negative 4. I end up getting a 0 here. Okay? And so now maybe we anticipate what's going to happen. What should I get out when I plug in negative 4? I should get out this remainder. Okay? So that's kind of the benefit of seeing that second time. Now, hopefully, I see what to expect. Right? So when I plug in negative 4 here, I better get out a 0. Otherwise, I did something wrong. Okay? Somewhere along the way. Right? Okay, so let's check it out. We got g of negative 4. Okay, negative 4 to the third power plus 2 times negative 4 to the second minus 7 times negative 4 and then plus 4. So negative 4 cubed. Okay, so I'm doing negative 4 times negative 4 times negative 4. I should get out a negative. Okay, don't put that. I mean, if you put it into your phones, like a lot of times people will get out positive and it just gets all messy. So just be careful there. But I do get a, let's see, 4 times 4 is 16. 16 times 4, 64. Yeah, so negative 64. Okay, and then plus, let's see what it is, negative 4 squared, that's 16. 16 times 2, so plus 32. Okay, but then plus 28 here, and then plus another 4. Okay, so let's check it out. Yeah, this should be 0, right? The reason I kind of know that quickly is, look at that. That adds up to 32. 32 plus 32, that's 64. Negative 64 plus 64, that does end up being 0. Okay, so that pattern still holds this time. And what you expect on the graph? Well, that means that the graph does intersect at negative 4. It intersects that x-axis. That's what we should expect, right? Because my y value is 0 there. So negative 4 comma 0 is a point on that graph. Okay, and we'll do it one more time. Okay, we've got 2 here. Okay, we've got 1, 2, negative 7, 4. Okay, again, those are coming from my coefficients up here. They are in decreasing power, right? I've got x cubed, x squared, x to the first, right? And then x to the 0 if you wanted to think about it that way. Okay, so I'm scrolling down. I'm putting my 1, 2 times 1, that's 2. And then just let me slow down a little bit. Notice, right, this is that 2, right, is the solution for what x minus 2 equals 0 is. That's how we kind of think about that. So if we see I think one of those videos with the synthetic division kind of said like x minus a, we're going to divide and do the synthetic division with that a, right? So if it's x minus that something, we're going to put that something right there for my synthetic division. Same thing applies here, right? This is like writing x minus negative 4. That's why we have a negative 4 here. Okay, so we've got 2 times 1, getting this 2 here. 2 plus 2, that's 4. 2 times 4, that's 8. Negative 7 plus 8, that's 1. 2 times 1, that's 2. 4 plus 2, that's 6. That's my remainder. Okay, that is my remainder. Just to get the polynomial, okay, we didn't do that step up here, but I didn't see the need to, but just to practice again, just to get the polynomial here. That first term is the decreasing, right? It's x cubed. So my first is x squared here. So it's 1x squared, okay, plus 4x, and then plus 1. 2 different ways to write this, but me personally, I like to just write remainder of 6. Okay, that's what's left over. Okay, g of 2, what should we expect to get out? Okay, g of 2, we should expect to get out 6. And let's just double check. Okay, so g of 2, we end up getting 2 cubed, okay, plus 2 times 2 squared, okay, minus 7 times 2 plus 4. 2 cubed, that's 8. Okay, this is also 2 cubed, so that's also 8, right, because 2 squared, and then another one, minus 14 plus 4. Okay, so 16 minus 14. 16 minus 14, that's 2 there. 2 plus 4, that's 6. It's like every time I get so nervous, I'm like, it better be 6. Like, that's just me. Like, I'm like, I really hope I didn't make a mistake or something along the way. So it is good to double check though, right? Because if you get two different numbers, you know you did something wrong along the way. And it's like every time I'm doing these videos, I'm like, oh, please tell me I didn't do something wrong. But anyways, good to see that these are the same. Okay? And then let's just double check on the graph to get that visual as well, right? We've got 2, and then, yep, it does intersect at that 6. So that is also a point on the graph. Okay? So I recommend kind of maybe pausing here and thinking about how you can kind of put this into your own terms. So it says, what patterns do you notice between the remainder, evaluating the function for a value, and then the point on the graph? So we've kind of talked about that pattern, okay? And we're going to talk about the pattern in a formal way on the back page, okay? So maybe though, it helps to kind of think about how you can word that, with your own words. How can you, if you were to describe that to someone else, how would you describe this? Okay, but again, I'm going to give you the formal definition. So maybe pause it here, do a little thinking. Okay, maybe try writing somewhere like, how could I describe that to someone else? Okay, that would be a good way to kind of think about this pattern that we just saw here. All right. So I don't know. Maybe, hopefully you've paused it, but maybe for me, it's like this number here, like this a. If I divide by that x minus a. If I plug that a in to the function, then I should get the same as the remainder, as if I were to do synthetic division with that a. Something like that, okay? But maybe you guys describe it differently, think about it in a different way. But it's important to, okay, what did Mr. Lee just say, right? Like what pattern did we just find, okay? But here we go. Let's do the formal definition of that pattern that we just found. Okay. All right, so what we just found is essentially the remainder theorem and the factor theorem. Now, they're very closely related, all right? And just one thing to keep in mind, without the remainder theorem, there is no factor theorem. The factor theorem is like a more specific version of the remainder theorem. It's just the factor theorem has more implications. I know, like, this one's technically going to be longer, but it's because it has more implications. But this is a specific time of the remainder theorem. Okay, so here we go. The formal definition. Okay, so that is if f of x is divided by x minus c. Okay, so that's like what we did, right? Something we had some f of x, a polynomial f of x divided by x minus c. Okay, then the remainder r is your remainder, equals f of c. Okay, and that's what we found, right? That x minus c, that was like the x minus 2 maybe. What we did is we ended up plugging in that 2 for f of x, so f of c and the remainder are the same. So that's that pattern that we just found. If this definition doesn't really help you visualize that, then that's okay. Go with the specific example, okay? Because sometimes seeing all those different, f's and x's and c's and all that and r's is just a little bit disorienting, okay? Look at a more specific example to kind of clarify that if you need. All right, the factor theorem, okay? So let's just think about what the factor part of that is, right? A factor is when you divide something evenly, right? We think about like, 2 is a factor of 8, right? Because I can do 8 divided by 2 and get 4, right? 4 is also a factor of 8, right? 8 divided by 4 is 2, okay? So if I think about polynomials, what that would look like is if I have a polynomial and I divide it by a binomial, right? 2 terms, okay? If it's a factor, it divides out evenly and I don't get any remainders. So in other words, this is the case, this is the specific case where my remainder is 0, okay? So for example, just to give you a concrete example, right? These were cases where my remainders were 0, right? These two, remainder 0, remainder 0, okay? So what we know, just to give you a heads up, what we're saying is that x minus 3 is actually a factor of this up here, right? X minus 3 is a factor of this because it divided evenly and I got no remainder here. It divides, if I did x this polynomial divided by x minus 3, I'm going to get this polynomial, no remainders. Okay, so that's what the factor theorem is looking at. That's when my remainder is 0. Okay, so here it is. F of x has a factor x minus c if and only if f of c is equal to 0. Okay, if and only if. So what that's saying is, f of x is a factor of f of x has a factor x minus c if this is true. Okay, but it also goes the other way around. If f of c is equal to 0, then x minus c has that factor, or x minus c is a factor of f of x. Okay, so and one thing maybe to point out, right, is this is the specific example where your remainder is 0 for this. Okay, on these in here. All right, so a few things come from this. Okay, remember, when something is a factor, okay, if we go back to what we did last time with graphing, okay, look at this, right? Let's go more concrete before I talk about anything further. So what happened in this case, right? X minus 3 was a factor. That's what the factor theorem is saying, right? Because I had a remainder of 0, okay, x minus 3 is a factor. That means that I have a an x-intercept at x is equal to 3. Okay, so that's what's happening here. In other words, it's a 0, right? In other words, it crosses the x-axis, right? However you want to think about it, it's a root, right? That's another way that we talk about that. So yeah, compare those two, right? You can't have one without the other. This kind of does interrelate into what we did last class. Okay, and that's what I'm going to talk about in here. Okay, so this has some implications, right? This one is a more specific example. It's a specific example when your remainder is 0, but there are further implications here. And here are some of those implications. Okay, so one is that C is a solution. Okay, now you could also say it's a root. You could say it's a 0. You could say it's an x-intercept. Right, all those things. Okay, another thing we can say here, right, another implication is x minus c is a factor. Okay, that is part of this, right? And then the last thing we can say, so it's basically three things. Three things come from the factor theorem. And then another way to think about it is that c, comma 0 is a point on the graph. Okay, so that c, comma 0 is a point on that graph. Okay, so that's the factor theorem. All right, and this next activity, okay, is just trying to get us to think about all the different implications, right, that come from these two pieces of information. So this is a little bit like kind of a word game in a sense, right? But what you can always kind of revert back to is the picture. Okay, these are all words, but maybe one word sticks out to you, and you can kind of link everything else. All right, don't forget the picture. All this is saying is, right, that C is on the x-axis. Okay, like in here, right? Just to remind you, right, with that 3, if I divide my polynomial by x minus 3, I get a 0. It intersects that x-axis. That's one point where I intersect the x-axis. All right, so given the polynomial f of x, okay, and f of 7 is 0, okay? F of 7 is 0. So when I input x equals 7, right, I get out 0, okay? Something to keep in mind. Is 7 a solution of f? Yes, okay? F of 7 is 0. My x is 7, right? Maybe we can write this. My x is 7. My y here, 0, okay? And that's a coordinate. 7, comma 0 is a coordinate on that graph. Okay, just getting, pulling out some information from that statement. So is 7 a solution? Yes, it's an x-intercept, so it is. Okay, is x minus 7 a factor of f? Okay, well, we just said that f of c is 0, okay, so f of 7 is 0, all right? So my c here in that statement is, in this one is 7. So is x minus 7 a factor? Yes, because that's what this statement is telling us, okay? So since I know this, f of 7 is equal to 0, f of c is equal to 0, then x minus c is a factor, or x minus 7 is a factor. Okay, if x is equal to 7, what is y? Well, it's telling us, right? I'm inputting it here. F of 7 gets me 0. Okay, remember, this is f of x. This is your y. Okay, so what is y? It is 0. Is 7, 0 a point on the graph? Yes, that's what we said up here. That's why I kind of broke down that information. So that's true as well. Okay, let's look at another one. Okay, given that the point negative 3, 5 is on the graph of g of x. Okay, what does that mean? Is negative 3 a 0 of g? Okay, so what happened when I plugged in negative 3 into my function? I got out 5. So, not a 0, right? If this was equal to 0, then it would be. But it's not. Okay, so this is no. So we'll put no. Is x plus 3 a factor of g? No. Okay, it's not, right? What was my remainder? Okay, remember what we're doing here, right? This is like when we plug in, what this is saying. This is saying when we plug in f of negative 3, we get out 5. Okay, does that fall into these lines? No, it doesn't. Okay, that's more of like the remainder theorem. So if I were to divide by x plus 3, my remainder would end up being 5. So this is a no. Is x plus 3 a factor of g? The answer is no. Okay, because again, if I were to do synthetic division with negative 3, okay, then I would not have a remainder of 0. What is g of negative 3? Oh, and this is g, by the way. I shouldn't have said f up here. Okay, g of negative 3 ends up equaling 5, right? I plug in negative 3, I get out 5. Is x minus 3 a factor of g? I don't know. I mean, that's a weird one because, I mean, we could test it, but we don't know what that polynomial is, so that's kind of a funky one, right? This doesn't tell us anything about 3, right? We know that negative 3, 5 is a point on that g of x, but we know nothing else about that graph, okay? So maybe, it could be, right? But nothing here specifically tells us anything about what happens when we were to plug in 3, okay? So maybe if it told us a point, right, like 3, something as opposed to negative 3, then maybe we could move forward with that, but we have no idea on that one. Okay, so we could continue with this kind of thinking, but a lot of this is the same. It's just different wording, okay? So I'll go ahead and leave these to you, right, because we've pretty much gone over these examples. It's just different, some of the different words, right, and everything like that. Okay? Let's do one of these with 5, 6, and 7. Okay? Let's do number 5. Okay? Let's do number 5, where we're actually going to do long division here. Okay? I know long division is not everyone's favorite. Everyone typically prefers synthetic division, but because of that 2x minus 5, it's actually going to be a little bit easier for us to do long division. Okay, so here we go. We're going to do it. 6, I should probably leave some more room. Okay, so let's do 2x minus 5. Okay, and we're dividing 6x cubed plus 17x squared minus 104x plus 60. What I'm doing in in long division first is I look at my largest term, okay, which is 2x, right? The largest powered term, right? This is x to the first, x to the x cubed. Okay, so 2x times what, which is what I'll put here, 2x times what will give me 6x cubed. Okay, so, well, 2 times what gets me 6? 3, right? And then x times what will give me x cubed? That's x squared. Okay, so if I were to multiply this times this, I'm getting out this. Okay, now what I do is I multiply that 3x squared to this. Okay, me personally, I like to write mine in parentheses. Okay, and I like to write that minus sign up there because I know that I'm going to be taking this and then subtracting this in here. At least I have that visual reminder. Okay, so I've got 6x cubed, 3x squared times negative 5. That's minus 15x squared. Okay, so I'm going to have a little answer here. This minus this, that's 0. Okay, we've got to slow down here. This is plus 17x squared minus a negative 15x squared. So this is actually like 17x squared plus 15. So this is 32x squared. And I'm going to bring down this right here, my next term. Okay, same process now. Okay, I'm asking myself 2x times what will give me this. Okay, so 2x times what up here will give me this value. So 2x times, well, first of all, let's just do the coefficient. 2 times what will give me 32. That's 16. Okay, and then x times x. X times x will give me x squared. All right, same thing. Multiplying in here, I get 32x squared, 16x times that. Ooh, big number. That should be 80, negative 80 x. Yeah. Okay. And negative 104x minus negative 80. Okay, so that's like negative 104 plus 80. Okay, should get me 24. Negative 24. Negative 24x. Okay? Because that's a really big negative number, right? We're adding back some of it, not all of it. Okay, we bring it down, plus 60 here. All right, 2x times what will give me negative 24x? Well, that's negative 12. Okay, negative 12. I've got negative 24x. I've got to make sure I remember I'm subtracting. Okay, and then negative 12 times negative 5. Look at that, nice and neat. 0 as my remainder. Okay, so remainder of 0. Therefore, 2x minus 5 is a factor of this polynomial. Something to keep in mind. Okay, so how would you determine, oh, we're up here. How would you determine if 2x minus 5 is a factor of f? Well, you would use long division. Polynomial long division. Okay? Now, here's the kind of trick. You can actually use synthetic division here, but you have to be kind of careful. Okay? Just to show you, I will just show you. You can do this, but I don't know. I don't recommend it. Okay? So you can use this right here. Plus 5, 2x equals 5 halves. You could do synthetic division with 5 halves if you really wanted. Okay, but I'm warning you, right? That's a lot of fractions, a lot of decimals if you were to use decimals. But you could set it up exactly like this, and you will get the same thing. Okay, and you bring down that 6, etc. But boy, I don't know about y'all. Those fractions don't sound fun to me. Okay, me personally, I'd rather do long division. But just so you know, you could also use synthetic. So yeah. Okay, is it a factor? Okay, well, that's what we just found. Okay, yes, it is a factor only because my remainder is 0. So, yes. Okay, and then we'll write because my remainder is 0. After performing long division. Okay, and so there it is. Maybe let's do one more. If you feel comfortable with this so far, I don't know. Shut off the video if you need. But I will go over one more. So let's go ahead and look at number 7. Okay. All right. So h of x is all this in here. Okay. Find h of negative 2 using synthetic division. Okay. Using synthetic division. Okay. So it's not saying to find h of negative 2 by plugging it in. Notice that. It's kind of getting you to find that h of negative 2, but doing the remainder theorem, essentially. Okay, so we've got negative 2. All right, synthetic division. Okay, we've got 8. It is decreasing, right? X to the 4th, x to the 3rd, x squared, x plus 24. So I don't have to fill anything in with zeros. And here we go. Okay, first step, I bring down that 8. Okay, and then I start. Negative 2 times 8. Negative 16. These two, add them together. Negative 30. Negative 2 times negative 30. That's positive 60. Add these two up, I get negative 11. Negative 2 times negative 11, that's 22. Negative 10 plus 22, that's 12. Negative 2 plus 12, that is negative 24. Remainder 0. Okay? So finding h of negative 2, okay, h of negative 2 is equal to that remainder. If I got 100, that's what my h of negative 2 is. If I were to plug it in, we could double check, right? I'm not going to, but if I were to plug in negative 2 here, you would still get 0. Okay? And what does this tell you about the function? Well, this is one of those cases where you do know, right, you have the remainder of 0, okay? Therefore, we could say that x plus 2 is a factor of h of x. That's one thing we could say. Okay? We could also say that negative 2 is a 0. Okay? Or x-intercept, or all those other words that you could use to refer to it. All right? That is the remainder and factor theorem. It's a really interesting thing. Your textbook online has the proof of it. It's not the most straightforward of things, but it is a kind of a strange property. But yeah, the proof's in the textbook. You could look it up. Yeah, it's for all you nerds like me out there. It's interesting, but I'm not going to go over the proof with you guys. Okay, but this does work every time. And remember, that's the whole goal of proofs, is to show that it works every time. And saying that, look, oh, you know, like, oh, it did it again. Oh, it did it again. You have to make sure everything's a variable, right, in order to prove things. You can't just say, oh, look, it did it this time. It did it this time. It did it this time. It should work for every time. Yeah, that's not how math works, right? You got to prove it for every time, right? And we don't have an infinite time to sit here forever for our whole lives and say that, oh, look, it works every time. So that's where algebra comes in with proving. So yeah, I just kind of went off on a little nerd rant there, but the proofs in the textbook, very interesting. That's all I got. Okay, you guys take care.